And here we are back. Hi, everyone. Thank you again for joining us for another session of JNation 2020. Here now we have Rafał from Hazelcast. Hey, Rafał, how's it going?
Hello, it's going good.
Yeah, wonderful. Thank you so much for joining us today. I know that you're going to give us a session today about caching and architectural patterns for microservices. Is that correct?
Yes.
Okay, that's okay. So I'm not going to take you too much time away. So please feel free to start. And we'll be happy to relay any questions that you might have from the audience to Rafał. So please feel free to send them over Slack or the YouTube channel. And please, Rafał, whenever you're ready, just go.
Thank you. Thanks a lot for the introduction. I'm super happy that I can speak to you right now from Krakow, from Poland, from my apartment. And I would like to tell you today about caching, and especially about caching in your microservice system. So what are different architectures for caching in your microservice system? But first, a few words about myself. So I'm a cloud software engineer working in Hazelcast. Before I worked at Google and CERN. I'm also an author of the book called Continuous Delivery with Docker and Jenkins. And from time to time, I do training and conference speaking, but my main job is I'm a developer. So I'm on the daily basis, I'm coding. Also, a few words about Hazelcast. So Hazelcast is a distributed company, and it is a distributed company in two meanings. First meaning is we are distributed because we produce distributed software. But second meaning is we are distributed because almost all our employees works remotely. So the situation like today, like speaking to people from my apartment is a daily thing for me. I just work from home every day. We have three products. You might have heard about Hazelcast. We call it Hazelcast IMDG, which is in-memory data grid, which is kind of a caching solution, a little more than caching. We call it cache on steroids because it has some more functionality. Second product is Hazelcast Jet, which is a library for stream processing. And the third one is brand new, is Hazelcast Cloud, which is basically Hazelcast put as a service in the cloud. All these products are open source, so feel free to use them as you want. Our agenda for today is pretty simple. There will be a very short introduction about caching in general, and then we will walk through all possible caching patterns that you can use in your system. While I'll be talking, I would like you to think about two things. First one is, which of this pattern do you use in your system? You must use one of them because this list is complete. And the second thing is, would it make sense for me to change to any other pattern? Would it make sense for my system to adopt any other caching pattern for my system? Going back to the introduction. So we all use caching. This is for two reasons. First one is the most obvious, it's for performance. So we have some long-lasting computation or anything that is time-consuming, and we don't want to execute the same for the same parameters. So we just cache the value and return from the cache instead. This long-lasting thing, it can be anything, call to the database, call to the external service, whatever that is time-consuming and therefore worth caching. The second reason for caching is maybe a little less obvious, but it's also a very valid case, which is to increase the resilience of our system. Just imagine it won't be for every system, but you can, even if your system is down, sometimes you can provide a cached value and the user may not even realize. As an example, if you think about Amazon and the recommendation service. So you as a user, you may see like an old cached value of the recommendation for you, but you wouldn't realize it. So even if the recommendation service is down in the backend, you may still be fine as a user. Now the thing for this talk is how the caching looks like in the microservice world. So this is what you see on this diagram is as very simple, actually, the very simple microservice system. So we have a lot of services, they have different versions, they can be written in different programming languages. They obviously use each other. So even a simple system is complex, actually. Now the question for this talk is, where is the right place to put your cache? Is it inside of each service? Or maybe outside as a separate unit in your architecture? Or maybe in front of your services? And that is what we will talk about. So let's start from the first, simplest caching solution, caching topology, caching pattern, which is embedded cache. Embedded cache looks as follows. Request goes to the load balancer. The load balancer forwards the request to one of the application services. And then inside the application service, there is a cache as a library. And the application check, okay, did I already executed such request? If yes, just return the cached value. If no, do some time-consuming business logic, put result into the cache and return it. So this is very simple, the simplest caching you can imagine. It's so simple that you can even think about implementing it yourself. If you use Java, that is how the code could look like. So we have our method process request. We check if such request was already in the cache. If yes, return it from the cache. If no, do some processing, put response in the cache, return the response. As simple as that. So you can write it yourself, but better don't do it. Don't do it because Java collection is not a cache. It is not a cache because it has no eviction policy, no max size limit, no statistics, no built-in cache loaders, no expiration time, no notification mechanism. So it lacks a lot of features that a good caching solution should have. Way better approach is to use some library for caching. And a very good library for Java is Guava Cache. And it has all these features which you can define in a builder and specify upfront. Another very good solution for Java is EHCache. Now, if you think about caching, we could move it even one layer higher and put it, not really write the code, is it in my cache, but put it in the application layer. And if you happen to use Spring, like most of the Java world, this is how you would use your caching. So you introduce a simple cacheable keyword, and then every call to this service method, get book name by ISBN, it will first check, okay, do I have this entry, do I have its ISBN already cached in a book's cache? And if yes, return the cache value. If no, only if no, execute find book in slow source. But be careful, because for some reason Spring uses concurrent hash map by default. So you're better off changing this to some other cache, like for example Guava. Now if we go back to this diagram we've seen just a moment before, this is a very, very good solution actually, but there's one problem with that. Imagine that the request went to the load balancer and then was forwarded to the application on the top. We executed some long-lasting computation, everything is fine, put it into cache, return the response. Now the same request goes to the load balancer, but this time it's load balanced to the application service, which is on the bottom. Now we have to execute the same long-lasting computation again, because these two caches, they are completely separate. They don't know about each other. That is why one of the improvements to the embedded cache would be to use embedded distributed cache. It's still the same pattern, it's still the same, like embedded cache, but it's some kind of improvement. So this time we will use a different library. Diagram will be the same, but they will use different library. So we will use Hazelcast as a caching provider. Now, Hazelcast is just a library, so you just use it as Guava or anything else. But it forms one consistent cache cluster with all the other caches. That is why no matter which application put value into the cache, this cache store in memory store is all together. And Hazelcast, as I told you, is just a library. That is why we can specify it, for example, in Spring, just use different cache manager, and that's all. That's all you have to specify to use Hazelcast as a caching solution in your Spring application. And here, let me show you a very quick demo on that. So this is a very simple application, which actually does nothing interesting, but this is exactly what you've seen on the slide. I define the cache manager as a Hazelcast, and the application does nothing more than start Spring application. So let me start the application. We need to wait a moment because it's always as Java, so it takes time. So you see, it already started the cache, one member. Now, if I start the same application once again, they should join together and form one consistent caching cluster. Again, we need to wait a moment because it's Java, but we support for the client, Hazelcast client, GraalVM, so you can make it faster with some Quarkus. But if we are presenting Spring, it's always a little slow. Now, but we already can see that it formed two members, they joined together and form one consistent cluster. So no matter which application now I will use as a user, they will both write to the same, not storage because it's in memory, but they will both share the data. Now, you may ask yourself, like, how is it possible that I've run it on my laptop right now? How is it possible that they discover themselves? How do they know how to find themselves? And I did run it on my laptop. That is why they actually could use multicast to discover themselves, as simple as that. But our IT production world is not that simple that you run everything on one machine. Not everywhere multicast is allowed. So then we thought, how it's possible to make Hazelcast members, Hazelcast nodes discover themselves automatically. And we came up with the idea of plugins. So we have a set of plugins, and depending on which plugin you start, then they will automatically discover other nodes using the specific API of the given environment. So for example, if you run it on Kubernetes, it can use Kubernetes API to find other members and automatically form a cluster for you, so you don't even have to think about it. And we have the same for all main environments. And even if you don't find your environment here, you can always start a Euroka server and piggyback on the Euroka server for the discovery. If you're interested in details, we publish a lot of blog posts, so just find it on Google, how to set it up, or Kubernetes Eureka, or wherever. So this is a solution for embedded cache and embedded distributed cache. So let's now look at the pros and cons of this solution. So from the good sides, we have very simple deployment, and you have very low latency data. You actually cannot do anything better than embedding your cache in your application. So you will never get better latency than here. And also, if you use embedded, you actually don't need any ops team needed or DevOps effort, because it goes together with your service, so you don't have to do anything more than you would do for just an application service. However, from the downsides, if you have such microservices, the cache management is not so flexible, because it scales up and down together with your application. Also, it's limited to JVM-based application. Actually, it's limited to the programming language of your service. Also, from the downsides, data is collocated with applications. It may not sound like a big thing. However, if you go to any big enterprise, it's actually a big problem for them. So they want you to have the data separately. So if you have like a big banking system, I can tell you upfront, they will use they won't use embedded cache. Okay, we closed the topic about embedded cache. So the next pattern, the next topology that you can use is client server. And client server is a little like, you can think of this as a database style. So you have your application, you have your cache server as a separate unit in your architecture. The diagram looks as follows. Request goes to the load balancer. Load balancer forwards the request to one of the application service. And now the application uses cache client to connect to the cache server. And cache server is deployed somewhere on your infrastructure somewhere, and the application just uses a client to connect to it. So if you compare client server to embedded topology, there are two main differences. So the first one is we have this guy on the diagram, and this thing on a diagram needs to be separately managed. Like you need to have to think about backup. It scales up and down separately. It needs some security and so on. So you usually will need some ops team or some DevOps effort. Generally, someone will have to maintain it. Obviously, you can automate it, but still it requires some effort. And the second big difference between this and embedded cache is this part. Is this part because now application uses cache client to connect to the cache server, which means that cache server can be written in totally different language than application service. It just needs a well-defined protocol, and that's all. So your application can be written in Node.js, and your cache server can be Hazelcast written in Java, but that's all fine. And that's a very common strategy actually in the microservice world. When you have this freedom of using your language of choice for your application, and now you have a lot of applications written in different programming languages, and you connect to the cache cluster or cache clusters deployed somewhere else. This is such a common approach that some cache providers, like the most known Redis or still used Memcache, they offer only client server mode. So you cannot. Redis is written, I think, in C, so you cannot embed it in your Java application. It just wouldn't work. So they only work as you have a well-defined protocol, you have your client library, and you can use it in client server mode. How to run it? Like if we stick to the Hazelcast, start a server. We have a simple SH script. So you start it. Again, it uses the discovery plugin, so it will automatically discover other members. If you use like a Kubernetes, like most of the world now going into the direction of Kubernetes, we provide a Helm chart. So with this one command, you set up the whole cluster, Hazelcast cluster, onto your Kubernetes cluster. How will like a client look like? So this should be the client configuration for your Spring application. We again configure the cache manager. We define client config. We say, okay, use Kubernetes plugin for the discovery. This is the set enabled true, and then return the Hazelcast cache manager. That's all. From now on, your application service will use your Hazelcast server deployed on Kubernetes. So we mentioned that in client server mode, you need to somehow manage this server part. And actually in like big enterprises, this part is usually managed by a separate team from what we see. And if it can be managed by a separate team, you can even move it one step further and move it not to the separate team, but move it into the cloud. So the cloud is still kind of a client server topology. However, it's so specific because your server part is not managed inside your organization. It's so specific that we can even consider this as a separate caching pattern. How it looks like. This is very simple, as I told you, to the client server mode. Just this part is in the cloud, so we don't have to think about this too much. We don't have all this management effort. We don't need ops team. We just actually pay for this to the cloud provider, which is usually cheaper than managing this by yourself. How the configuration will look like for this? So the code, if we stick again to this Spring example, the code will look like this. So we have some discovery token. So you create your cluster in the cloud. You get discovery token and cluster name and password. You put it into your configuration, and it's automatically discovered. What is interesting that obviously there is no static configuration here, which is good. What is also interesting is that it's not only Hazelcast working this way via discovery tokens and so on. Now, from what we see is most cloud-based solutions like, I don't know, Elastic Cache or anything you will find on the cloud right now, it works this way, that you create a cluster, they give you the discovery token, and that's all. You don't need anything more. Let me show you a very quick demo on how to set up a cluster, Hazelcast cluster in the cloud, and how to use it from my laptop. So if you would like to start the Hazelcast cluster, you go to the cloud, hazelcast.com. You set up your free account. That's no problem. Then you click on new cluster. You give it some cluster. You give it some cluster name, and you select the underlying provider, which I will speak about in a moment. This too will come soon, but this is important thing, and I will explain it. Why you need to choose the underlying cloud provider, and why does it matter for you? You select the region. Select the cluster size, some other configurations, and just create cluster. And then in a moment, your cluster will be created. While it's still pending, I will explain you why you need to select the underlying cloud provider. So the thing is, we don't provide the infrastructure. And it's done on the purpose. It's also because it's easier, but it's on a purpose. Because people who will use cloud, I mean, we are in the caching domain, which is a very low latency domain. And that means that you cannot, if your applications are in the one cloud provider, you don't want your cache server to be in another cloud provider, because that would be slow. Your latency would suffer. So you want to create, if you use AWS, you would like to create your Hazelcast cloud cluster, which is also on AWS, so they are in the same cloud provider. What's more, they should be in the same region, actually. But that's not even enough. There is even one layer more. They should be actually in the same VPC. That is why we provide a way to do a VPC peering between your network and the network in which we create a cluster for you. And this way, there is even no one router hop between your applications and the cache cluster we manage for you. And that is very important because, as I told you, we are in the domain of caching. We are in the domain of in-memory data grids. So where the latency is even more important than your database. Our cluster is running. How to configure this? You can click on configure clients, download like predefined clients in different programming languages. I will just need, for this example, I will just need discovery token and group password. So let's look at our code, which I will run on my laptop. Yeah, this is our cache configuration. So if we look at this, so we have to copy the discovery token and the password. And obviously change the cluster name. And with this configuration, I can start the application. And we should see in a moment that it connects to the cluster. Now, obviously, I'm not doing this right because it's just my development environment, because I'm connecting from my laptop into the cluster, which I think deployed in US or something. So the latency will be very high. But you can see it's just an example. So it connects to this free cluster with 3 members, which I created in the Hazelcast Cloud console. We offer free clusters, as everyone is used to now in the cloud. So I really recommend playing with that. It's really nice. And you can create a free tier cluster for free. Coming back to our presentation, so these are the pros and cons of using client server and cloud cache topology. So from the good sides, data is separated from the application. As I told you, it's a must go for big enterprises. They want to have their data separated from the application. From the good sides, we also have control over the management of caching, so we can scale it up, backup. Everything is separated from your application, which is actually a good thing. Also, from the good sides, it's programming language agnostic, so your cache can be written in one language, your application another. We have well-defined protocol. That's all. From the downsides, you need separate ops effort, or you need to pay for the cloud. You have higher latency, and server network requires adjustment, which I just explained. So if you are running on-premises client server, you have to think about it. Your cache needs to be in the same network as your client applications. If you're using cloud solution, that is what I just explained. You would like to have the same cloud provider, the same region, and the same and the VPC, which is paired with your VPC. Okay, which we covered the embedded and client server caching patterns. And you may say, like, now, it's like it's all, everything you're talking about is so old. Embedded cache is a very old strategy. Client server, we've seen it for years. So now we will see something completely new. Cache as a sidecar. So this time our diagram will be Kubernetes specific, because sidecar pattern is mostly seen in the Kubernetes environment. It's only in the containerized environment, but it's like in this containerized world, it seems that Kubernetes has won this war. So there is much less people using like Docker Swarm or Apache Mesos. It's Kubernetes is number one. That is why this diagram, I made it Kubernetes specific. But even if you don't know Kubernetes, a very short introduction about Kubernetes. So in Kubernetes, a deployment unit is called a pod. And in a pod, you can have one or many containers. Usually you have just one application container, which is your application with the business logic. But sometimes you add an additional container. And this additional container, it can be, for example, a logging agent, which will forward your logs from your application somewhere else. So some kind of additional functionality. And this additional container is called a sidecar container. So always when you have multiple containers, one will be your main application, the other will be a supporting feature, and this supporting feature is called a sidecar container. Now, going back to our diagram. So it looks as follows. Request goes to our system. It goes to the Kubernetes service, which is kind of a load balancer. Kubernetes service forwards the request to one of the Kubernetes pod. In the Kubernetes pod, it's application container, which takes the request. Application container uses cache client to connect to the cache server, but this cache server is actually deployed as a sidecar container. So it's always available in the same machine. It's always available at the local host. So this solution is kind of a mixture of client server and embedded mode. It somehow resembles embedded mode because it's your cache and your application, they are deployed on the same physical machine. So they actually share resources and everything. They are also scaled up and down together. There is no need for discovery because it's the same machine. You can always use localhost. But this is also similar to the client server because you can use different programming language for client and server. No problem here. They are separate containers, separate running applications. And after all, they use cache client to connect. And there is some isolation between the application and cache data. The isolation is at the container level. How it would look like, how this configuration would look like in the code. So this is, again, the Spring configuration. So we define a client configuration. We use kind of a static configuration, but it's because we use localhost. However, we know that it's not static in general because it's just that we know that the deployment will be in such a way that you will have this cache always at the localhost. How your Kubernetes configuration looks like. So you have your deployment, which specify the pod template, and you always have two containers. The first one, application, is your business logic, so it will always be different depending on your service. And the second one is Hazelcast server, which is always the same. And this is your deployment. Obviously, all these cache containers in different pods, they form one consistent cache cluster. That doesn't change. Pros and cons of sidecar caching. So again, the configuration is very simple. You as a developer can configure anything. It's programming language agnostic because we use cache client. Low latency because they are deployed together. And we have some isolation of data and applications. And from the downsides, it's limited to container-based environments. I wouldn't say it's actually a downside. It's where the direction the world is going to. So that's how the world of IT looks like at the moment. The management is not flexible again. So application and cache, they scale up down together. And the data is collocated in the same application pod. So actually the data is on the same machine. Okay, the last pattern for today is something completely different. It's completely different because so far, from what we've seen, application was always aware of caching. This time we will do something different. We will put the caching in front of the application, like this. So now the scenario is as follows. Request goes to our system. It goes to the load balancer. And now, just before the load balancer or just after the load balancer, we have a cache. And only if the request is not found in the cache, it's forwarded to the application. So the application is not aware of the caching. Obviously, now the caching needs to be on some, probably nowadays, HTTP protocol level. A very good solution is to use Nginx, which can be used as load balancer. It can be used as a caching. So to run an Nginx as a cache, the simplest you can define is where to store your cache data. Nginx is a good solution because it's mature. A lot of people are using Nginx, so you can be pretty confident to use it on production. Nginx has some problems, like it's only for HTTP protocol, which is nowadays probably not a big deal, but it's not distributed and not high available, which is a big deal. So you usually, if you have a big system, you would like your cache to be distributed and to be high available. And also the data is stored on a disk. It's not really stored on a disk, but it can be offloaded to the disk. If you, for example, use Hazelcast, you are sure that your data is in memory, so you are sure about the performance. And Nginx can be fast, can be slow, depending if your data was offloaded to the disk. You could use, Nginx has some way to write modules, and you can use some modules as a backend for the caching. However, like for Hazelcast, it does not exist yet, and for Redis, it's not very mature, so you can be limited here. Now, we can even like go one level more and put it all together and propose reverse proxy sidecar caching, which will be the reverse proxy caching, but using Sidecar. So this will be our last variation of the caching for this presentation. So this is how it will look like. So again, it's limited to Kubernetes as with the Sidecar, and now it will work like this. Request goes to the Kubernetes service, which load balances the traffic to one of the Kubernetes pod. However, now it's not the application container that receives the request, but a reverse proxy cache container, which intercepts the request, and only if the value is not found in the cache, it forwards it to the application container. If the value is found in the cache, just return the result. So again, application is not aware that it's cached. Now, this whole idea, like about reverse proxy caching and about application not being aware of the cache, it has some good and bad sides. So starting from the good sides. So good thing is, and why you would use it. So imagine like your microservice system. This is a diagram from the beginning of this presentation. So you have a lot of services. They are in a different versions. They are written in different programming languages, and they use each other. So it's getting complex. And if you have some experience with microservices, you know that it's very quickly growing to a really hard to maintain system, because you can easily have like 50 microservices, and they have different versions, and it's just difficult. So the thing about reverse proxy caching is that you can look at this system from like an overview of the system on such a diagram, and you can say, I would like these two services to be cached. and you don't even go to the core of the services. You don't even change a thing. And you are adding a functionality, and that is the whole beauty of this approach. And it's so, so nice that you can, in a declarative manner, define, okay, I would like to service 2 version 1 and service 1 to get cached. That's all. So this is why I would use it. You can think how it would look like in a Kubernetes configuration. So usually you will need actually 3 containers. Now, 2 containers, 1 init container. So let me explain it. Maybe let's start this time from the bottom. So from the bottom, you have an application container. This does not change. This is your web service. This is your application service with your business logic. Then you need this caching proxy container. So this will be this container that intercepts your request, check if it's cached, and then return the cached value or forwards this to the application. And you will also need some init networking init container, because normally it's the application that would receive a request. If the request goes to the pod, it's the application that has the port open. However, we need to change it. We need to change the IP tables so that the request from outside on the port opened by the application doesn't go to the application, but it goes to this reverse proxy cache container. And the requests from inside the pod, they go to the application. And we can tweak it with a simple script put in an init container. That is the whole script. So please change the IP tables. Now, again, if you look at this diagram, you may say, okay, I've seen a diagram like this, and it is similar to the diagram from Istio, because that is exactly what Istio does. The Istio is more generic. It's not for caching. It's for network security, where to which version of the service it should be. Your request should be forwarded. So it's in a declarative manner. You can change it. Now, the Istio. This is the slide. The Istio wanted to add caching. And that is the slide I was always presenting, like that. They tried to enable caching, but they opened this issue on 3 years ago. But now I have a new slide, because they just last month, they closed this issue. So, which means that Istio, which is getting on popularity very fast, implemented caching. So you will soon be able to use reverse proxy sidecar cache in the Istio itself, which will be very good. Because other than that, there is no major solution for reverse proxy sidecar caching right now. We implemented in Hazelcast a prototype, but it's far from something that could be useful on production. Now, I told you it has this idea of reverse proxy caching. It has some good sides, but it also has some bad sides. Because it may sound like a great idea, but there is no such thing as a free lunch. So if you detach the caching from your application, so your application is not aware of caching, there is one thing that becomes more difficult, and that is cache invalidation. And if you look anywhere on the internet, what is the most difficult part with caching? It's cache invalidation, which means when to decide that the values in the cache are not valid anymore, that they are stale, that I should go to the database directly, not to the cache. And that is very difficult in caching in general. Now, if your application is aware of caching, then you can use some business logic to evict some values from the cache. Like in a Spring, you would do something like this. Please, if something happens, that just remove these values. That is all fine. However, if we use reverse proxy caching, you are limited to some standard protocol level things like timeouts, ETAGs, basically timeouts for for cache invalidation. That may be good enough or not good enough. It will depend on your use case. Short summary about reverse proxy and reverse proxy sidecar caching. So from the good sides, and the reason why you would use it is it is configuration based. In a declarative manner, you can decide what is cached. That is great. It's programming language agnostic. It's everything agnostic because it doesn't even touches your application. And it's very consistent with the containers and microservice world. That is actually the direction I think now the microservices are going, Kubernetes with the Istio and everything like that. We need to manage somehow these microservices, and that is the way to manage your microservice architecture. From the downsides, we already mentioned it's difficult to do cache invalidation. There is no mature solutions yet. I think it will soon be mature with the Istio, but still, I think they even didn't release this caching yet. And this is protocol based, but this is not a downside. It's something you just need to accept. And like this, we walked through all possible caching patterns that you can use in your system. So as a very short summary, I will not repeat anything I already said because that could be boring for you. So what I proposed as a very short summary is a quick decision tree, which is simplified, but which can help you, can help you choose caching topology for your system. So I would start from the question: does my application needs to be aware of the caching? If no, then is it container based? If no, use reverse proxy. If yes, use reverse proxy sidecar as soon as there is a mature solution available. Now, if your application needs to be aware of caching, then do I have a lot of data or some security restrictions? Basically, is my company like a big banking industry? If no, does it need to be language agnostic or dual run containers? If no, use embedded distributed caching. If yes, use Sidecar. Now, if you have a lot of data, you work in a big banking industry, then the last question you need to ask is my deployment, is my infrastructure cloud? If no, use Clientserver. If yes, be consistent with this and use cache as a cloud. So this is a very, as you see, like it's maybe oversimplified, but at least gives you the direction where to look for the right architecture for your caching. As the last slide for this presentation, I would like to just mention a few resources. So the first one is the blog post of how to set up Hazelcast as a sidecar. Second one is our prototype of this reverse proxy sidecar caching. You can look at this, but it's very, very prototype based, so better not use it in production. Third resource is not really related to this talk, but it's a very good blog post about caching in general. And the last one is a very good video talk about how to set up Nginx as a reverse proxy caching. And with this last slide, I would like to thank you for listening. It was a pleasure to speak to you.
Hey, Rafał. Yeah, thank you so much for the wonderful presentation. I think we're not going to have any time for QA, but for the feedback we're seeing here on Slack, people really enjoy your decision tree in the end. I think it's a very interesting concept, so at least it will guide you a little bit when you have to make some decisions, right?
Yeah.
Well, Rafał, I'm going to let you go. So thank you so much for joining us today. And thank you so much for the wonderful presentation. And I'm pretty sure that if people in the audience have any questions, they can reach you out on Twitter.
Sure.
And then you can answer them over there, right?
Yes, sure. It will be a pleasure.
Wonderful. Thank you again, Rafał. So see you next time.
Yeah, thank you. Bye.
Bye-bye.